Okay, thank you for the introduction, Verika. Hi, I'm Andrei. I'm gonna talk a bit about the basic research that we do at Bitdefender today. But first, maybe a few words about the company. We're a cybersecurity company founded in 2001 in Romania. This is our nice HQ in Bucharest, but we also have one in Santa Clara in California. More than 50% of our employees actually work on research and development, and this is a rare thing usually in the industry. And a very cool thing about how we work is that we actually also partner with entities like NATO or Europol to kind of catch cyber criminals. So if you ever saw like a hackers movie, yeah, we do that in Bucharest. So that's really cool. And today I'm gonna be talking about some directions that we work on the machine learning research team, so we're quite diverse. For instance, we have Elisabeta and Stefan, which are working on deepfakes. Stefan is also somewhere here in the crowd. Florin, Ioana, Dragoș, and Marius are working on LLMs. Then we have Elena, Antonio, Cristi, and Radu, which are working on distribution shifts. Florin is working on reinforcement learning, and I'm currently interested in geometric deep learning. So this is kind of the whole crowd. If you find anything, any one of these topics interesting, please shoot us an email. We're very friendly, I promise. Yeah. So today I'm actually going to be talking about anomalies. So as I was saying, I'm currently more interested in geometric deep learning, but I started doing research with anomaly detection. And we have research direction which I find interesting, and maybe you guys will find it interesting as well. So whenever I speak about anomaly detection, I like to show this quote from a very old book, but I don't really know if you can actually define an anomaly in a better way. So it says that an anomaly is an observation which deviates so much from the other observations as to arouse suspicion that it was generated by a different mechanism. So this is a very vague statement, and I think this is actually intentional because anomaly detection is somewhat of an ill-defined and vague problem to solve. So as a more visual representation about what this quote is about, let's assume that we have this data generating process. So this is the 2 moons data set, where you have this nice curves, and then you have some points which kind of lay on the curves, but then you also have some red points which seem to be out of place. So we can say that these red points are generated by some other different mechanism, and we would want to be able to tell that something weird is going on. So be able to identify what's happening there. So when we do machine learning, we usually are in this classical machine learning approach. And we also have classical outlier detection or anomaly detection approach, where we basically have some kind of a universe. So for instance, we could talk about pictures, we could talk about text, we could talk about any kind of modality. And then we have some training data and some testing data. And what's different from the normal supervised way of training our models, where the training and testing data come from the same distribution, is that now the outliers kind of come from this place, which is a bit weird. So yeah, one way of actually doing anomaly detection and the classical one-class classification way would be to just learn a distribution of clean-ish data. And then ask the model if, okay, is this new sample that we have here similar to the distribution of clean data that we know? And I'm saying ish because in practice, most of the models are kind of robust to a certain percentage of data contamination. So you can have some outliers in the training data, but usually our main assumption is that the training data has a very low degree of contamination. And in practice, this means something like between 0.1% to maybe 10% at most. So one work that we did in this kind of like a classical way of doing anomaly detection is this method where we use self-supervised training on text data to actually be able to detect novel concepts and anomalies. And if you're not familiar with self-supervised learning, it kind of goes like this. So basically, we have a volume of data, and then we're corrupting parts of our data. And we're kind of trying to learn about how the data distribution looks by predicting some of our data where maybe basically filling the parts which are missing. So for instance, in computer vision, something like predicting some part of the face which was intentionally occluded would be a self-supervised task. And then in natural language processing, you have the causal language modeling task, which is like the next token thing that we do when we train large language models. And we also have some other things that we can do, such as noise contrastive estimation. And with this in mind, we kind of tried to use this kind of an approach to be able to discriminate between normal text and outliers. So this is the whole pipeline right here. And the way that we do it is that we generate this kind of masks that we use to pick some positions in the text, in the input text that we want to corrupt. And then we use a data distribution that in practice is usually just a uniform distribution over the whole vocabulary to replace the tokens which were masked with some other samples. So if we have the input, they were ready to go, we do the masking, then we sample from a distribution, we change the text and they were prepared to depart, and then we have a transformer which needs to say which token is original and which one was replaced, and also we want to kind of predict the mask which was applied over the input text. So, I mean, this is kind of similar in a way to like a GAN, a generative adversarial network, but we don't really do the min-max thing. We really just do cross-entropy. So we just have a binary classification and a k-head classification step. So the assumption here is that the network is likely to predict replaced for tokens from an outlier, even if the sequence is not corrupted. So what we do in practice to actually do anomaly detection with this model is that we feed the uncorrupted text to the discriminator. So we throw away the random distribution or the learned distribution. We don't mask anything anymore. And then we compute the probability for the tokens to not be corrupted. And finally, we get an anomaly score by averaging all of these probability at the end, so we can have the decision if some text is an anomaly or not. And in practice, at the time, this really improved the state of the art. So I think this was actually the first self-supervised method on text. And you can also see that we're kind of robust to dataset contamination. So even if we have about 10% of the dataset contaminated with outliers, we basically have a better performance than the other methods at 0%. So this was a very good way of actually doing it at the time. And one very cool thing about training the models in this way is that you also kind of get like an explainable AI mechanism for free. So in the first example right there, we have news topics, and the setup is that we train our model on some sports news data set, and then we feed it some outlier which comes from the world. And you can see that it kind of looks at words such as Democrat and politically motivated, and it says that these are strange in the context of sports, because usually don't speak about politics when they speak about sports, or they shouldn't at least. And maybe a thing which is even more interesting in my opinion is the fact that when we trained this model to be able to identify some author, it was actually able to pick up on some details that forensics analysts usually use to tell if someone wrote two texts. So if you have a new text and you would like to tell if it was written by a person or not, people usually look at stuff like punctuation, and it was actually able to pick up on this kind of things without us giving it instruction to do so explicitly. So this was a pretty cool result. So overall, self-supervised learning is very powerful for sequences. We're kind of robust to this contamination thing. And we also get an explainable mechanism for free, which is in practice quite important, because if you use it on something like log sequences, for instance, you would want to be able to tell where things get weird. Okay, so now going a bit further, let's just imagine that we want to train a model to be able to detect these cute capybaras right here, right? So this is our inlier distribution, and then we would want to say something like, okay, we have a dog, this is weird, a dog shouldn't be here, maybe call like the zoo manager and get the dog out. But then we have things like global warming, so the environment of the poor capybara could just change, and I mean, it's still alive, but it's not very happy anymore. But the main point that I want to make here is that if we have these examples now with a model, an anomaly detection model trained on the first examples, this would maybe come off as anomalies. So it would pick up on the background, and it would kind of learn this kind of a spurious correlation between having a capybara in the picture and actually being in the forest. And even worse, maybe if the dog gets like a capybara mask and also has the water background, it would say that that's actually not an anomaly because it's focusing more on the style than the content of the image. So now we're kind of interested in this out-of-domain generalization approach, where we actually don't only have training and testing distribution, which comes from the same place. We have multiple and different distributions for both training and testing. And we wanted to have an experimental setup for this in the anomaly detection context. So this thing is very popular in generalization, like supervised learning generalization, for instance, but not so popular with anomaly detection. So we made this data set collected from some network logs. And what we wanted to do was to have a continuous stream that spans over a large time. So this collection, I think it has something like 10 years of data. And the shift in the data distribution occurs naturally. So the anomalies are basically some attacks gathered from some honeypot, and then we also have normal system behavior. So our protocol is training on the YYD, so the normal splits from 2006 to 2010. And then we also have two splits, which is a near and far split, depending on the chronological order. And we looked at things like how the features change, and also what we can do to actually maybe try to alleviate this. So if you look at this violin plot of one of the features, you can see that at each year, both the inliers and the outliers kind of look different from the same feature. So we do this with Jeffrey's divergence, again, at a feature level, and you can see that if you go further in time, it's going to be more different. We also have some visualizations. So this is a t-SNE plot. So in brown there, you can see data from 2011, and the other ones are kind of different things. And we also use something which is called the optimal transport dataset distance to see if at the whole dataset level things are changing, and yeah, they are. So here you can also see that if you go further in time, everything is going to be a bit more different than what you know. And one observation that we made is that all of the anomaly detection models fail to generalize over this distribution shift. So the performance actually drastically drops when we train with data from the past and then we test on the other splits. So you can see that it goes from something like 80% to something like, I don't know, 35%. And we're taking the bird, which was kind of thought about as an anomaly detection, to actually see if we can improve things a lot. And some very naive ways that we used was to just train a model in an IID way. So basically, we just retrain the model at each year, and this is kind of our baseline. We tried to take the weights from the previous years and then fine-tune with the next years, and this is actually making things worse. But one thing that seems to work is to actually do model distillation. So you basically have two models, and then you distill the knowledge from one model to the other one. So the improvement is significant, but this is a very naive approach, and this is a very naive way of doing it. So the key insights here, once again, are that we have this chronological distribution shift data set that we analyze, and we also propose some ways about how you can fix this kind of issues. So finally, I want to talk about novelty detection and robustness. So if you remember this picture, maybe one way to actually be able to tell the difference between capybaras and dogs would actually be to just ignore the background, so ignore the pond, ignore the forest, and things like cacti and so on and so forth, and just focus on the thing that we actually want to classify, so on the content that we actually want to think about as being normal. So we kind of shifted away from anomalies. We say that we do novelty detection, and we're trying to be robust to some classes of anomalies. So in this case, the style changes, so we want to be robust to the style, but then we want to be able to classify the content. So another example from the paper is this domain net data set where we have things like pizzas and bananas, which could have different styles. So on the y-axis, we have the content, which we are interested in. So banana versus pizza, and then we have the style real or painting. And if we add a new style to the data set during test time, in this case it's the sketch style, we would want to be able to tell that, okay, this is still a banana, this is still a pizza. But then if we add some new content, we would want to be able to tell that the laptops are basically anomalies in this case. So we say that the style is not relevant for our task, and then the content is the thing that we're actually interested in. So basically, we're leveraging the environment idea, which is very common in the out-of-domain generalization literature. So an environment is basically the samples with a particular style category and any content category. A style category are some factors that hold only in one environment, such as real versus painting. And then the content category is factors that hold across all of the environments, so banana, pizza, laptops, and so on. And we want to be able to detect novel content ignoring the environment biased features. So a thing that seems to work very well in practice, which was a bit surprising because this is a very simple approach, is to actually just take the features from a pre-trained model. So you get your photos from all of your environments, you forward them to something like a ResNet or a clip. You take the features and then you compute this variance score, which is the variance of the Wasserstein distance between different environments. And then you re-rank all of the features based on this variance. And the main intuition here is basically the fact that in this way we can kind of eliminate the features which are biasing our downstream model, so the environment features. And this seems to work very well in practice, so we can see that if we use 100% of the features, we get something like a 56% rock score, but then if we eliminate 50% of the features, we go up. And this is consistent with multiple downstream models. So we basically just extract all of the features from our data set, then we re-rank them, we eliminate them, and we use this classical anomaly detection methods, and you can see improvements all around. And we also wanted a synthetic setup where we can kind of control the spurious correlations between the environments that we have and the objects that we're interested in. So we made this synthetic data set called CocoShift. We basically take objects from Microsoft Coco, which is a segmentation data set, and then we take some backgrounds from places and we just put one against the other. And I mean, this is kind of weird. You can see flying pizzas on, on something like a river side, but this is very useful because we can actually control the level of spuriousness in the data. So for instance, if you get something like 95% spurious, you will basically always have a lake in the background whenever you see a pizza. So what we found out is that all of the env-aware ranking methods are actually doing a very good job on extracting content and ignoring style. So in this experiment right here, we basically do 2 forwards through the model. We only take the banana with the black background, and then we only take the environment. We forward them, we concatenate the features, and then we try to re-rank them with our methods. And it seems to work very well. So there's also some stuff like PCAs there, which are not environment aware, and they tend to work a lot less. So finally, I think this is a very interesting problem. And some key insights from this work is that you can actually, and you should actually, try to separate the content from the style of your pictures or of your data set in general. And you can do this quite easily with methods like Stylist. And then a very good thing to do is to actually drop the things which are common between all of the environments. And then you can also do things like synthetic data sets to actually validate that your method is doing the right thing. So one major drawback of this approach and all of the environmental aware approach is that we actually need style labels, and we would really want to not need style labels because we want to do unsupervised anomaly detection. And the question is if we can extract styles in an unsupervised way. And we're working on this. If you're interested in this kind of works, you can say hi to Christy, which is somewhere there in the summer school, and we'll be here for the whole summer school, and you can talk with him more about this kind of problems. So this is it from my side. It's really cool that there are so many people here with so many diverse backgrounds, and I'm very happy that we were able to actually help the summer school. And if you're interested in any of the topics that I've presented, you can check out our website, and we also have a company page on EEML, on the EEML website, where maybe you can see things like products that we offer and other things that we do. And we're also going to have a stand during the poster session, and we're going to be here all week. So yeah, enjoy the summer school, and maybe do we have time for 1 or 2 questions? Yeah, so in this case, it's background, but it can also be something like the style of the image, like in this case, real versus painting, for instance. So when I say style, I kind of mean any kind of spurious feature which could produce some kind of a spurious correlation in your model. So, yeah. So if I understand correctly, well, this is across the whole image, right? Because this is not synthetic. This is actually the same concept, but in 2 different styles. So and it also has something like a sketch there. So I'm not sure if maybe I didn't understand the question. Oh, yeah. We also, yeah, so these are all of so the main net is the one that, and Coco Shift is the synthetic one. So the first 2, I think, are real, and only the last one is actually fake. Thanks.